All right, so we have been talking about electrons in this section, and you looked at a simulation that taught you about how electrons can move between energy levels. So now we're going to talk specifically about what's happening in this system at a macroscopic scale. What would we see while these electrons are doing this? So if you're doing this on Notability, great, you have access to color. If you're doing this on paper, go ahead and pause this video really quick and go run and grab yourself a couple different color, either pens or crayons or colored pencils, whatever you need, but you're gonna need at least 3 colors. You do not have to use the same colors I'm using, but you wanna make sure you can differentiate between your arrows. All right, so essentially our electrons are basically like toddlers, or kind of like high schoolers. Y'all kind of act the same sometimes. So hear me out. Electrons are basically like toddlers because toddlers walk around with some amount of energy, right? But you give them some sugar and they go nuts. They get really excited. They run around all these places. They're basically just on a sugar high. But with every sugar high comes a sugar crash. So eventually toddlers will come back down to that energy level that they were at before, and they're going to need to take a nap to refuel, right? So electrons are kind of work the same way. Electrons can be excited into higher energy levels if they are given the exact right amount of energy. So you saw that in your simulation, that energy levels are quantized packets of energy. So if electrons get excited into a higher energy level, they can do so if they're given the right amount of energy. So let's write a little bit of notes to ourselves over here. All right, so if electrons move from a lower energy state to a higher energy state, we're going to call this absorption. They are absorbing energy just like toddlers are absorbing the sugar into their system. That's pushing them to a higher energy state. So I'm going to represent this using a blue arrow. Let's say that my electron moves from n equals 1, this lowest possible energy state here. Let's say my electron started at energy level 1 and it pushed itself up to energy level 2, n equals 2. That arrow would look like that. But it's also possible that it could push itself all the way up from n equals 1 to n equals 3, right? So I'm going to use a little pink dot to represent my electron here. So this would be an electron absorbing energy in order to push itself to an excited state. So what happens when an electron releases energy? Well, just like a toddler coming down from their sugar high, an electron can relax or drop back into a lower energy level as long as they release the same amount of energy that it took to get absorbed in the first place. So let's write ourselves a note over here. All right, so if an electron releases energy, we call this an emission. They emit energy. So that electron could fall back from n equals 3 all the way down to n equals 1. We're going to represent that with a purple arrow. And subsequently, let's say our electron started at energy level 3, or got excited to energy level 3, it is possible that it can fall back only to energy level 2. So I'm going to represent that with a red arrow. And you'll see why I want you to do this in 2 different colors in just a little bit. So both of these arrows represent an emission. So how can electrons absorb energy? Well, we've been talking a lot about energy in the past couple of days, right? So electrons can gain energy from the surroundings in a few different forms. One way that we've already seen that electrons can gain energy would be in the form of heat. So we can use heat to excite these electrons. You can also do this using electricity. You could even use this, you could even excite electrons by giving them other light energy. There's an entire branch of chemistry called photochemistry that's dedicated to just what happens when we shine light on stuff. It's pretty cool. There's other ways that we can do this, but these are the main 3 that we might focus on. So I'm just going to put those 3 in there for now, call it ECT, etc. for more. So if electrons are gaining energy, like I said, we call this absorption. But when electrons fall back down to lower energy levels, we call this emission. They release energy, they are emitting energy. So let's say that I had you take a big swig of water. I had you throw a bunch of water in your mouth, but I told you not to swallow it. that water would be sitting uncomfortably in your mouth for a while, right? Eventually you're going to want to spit it all back out. So that's kind of what it's like for electrons. Electrons have to take in a big swig of water. They get excited to a higher energy level, but eventually they want to come back down to their lower energy level by spitting out that energy. So when electrons release energy, or essentially spit it out, they always do so in the form of something called electromagnetic radiation. I apologize, I should have given you a bigger line here. So if this electromagnetic radiation is in this very teeny portion of the electromagnetic spectrum in the visible light range, we are able to see it. So if electromagnetic radiation is in the form of light, we'll be able to see it. And this is kind of what we're going to focus on. Yay, light, woo! So, if I scroll down to the bottom of the next page, you'll see a copy of the electromagnetic spectrum here for you. So energy is increasing going from right to left. An increase in energy goes from right to left. We're going to talk about energy and its relationship to wavelength. So if you take a look at this visible light right here, it's actually giving you measurements in hertz. It's not giving you measurements in wavelengths. Hertz is relating to frequency. Frequency and wavelength are inversely proportional. So if we look up at the wave that you see right here, wavelength is that measurement from peak to peak of a wave. Hopefully you learned about that in physics. So something that is a short wave means that your peaks are really close together. Something that has a really long wavelength means that your peaks are pretty far apart. So we measure wavelength in terms of meters, or if they're really small, nanometers. So if I go over to the short wavelength section right here, nanometers, oops, come on, pen, work with me. Nanometers is actually 10 to the negative 9th. That's the measurement of it there. 10 to the negative 9th. So this is incredibly small. So short wavelengths could then correspond to high energy, because energy increases as you go from right to left. So if something has a really small wavelength, it has a really high energy. If something has a really long wavelength, it has a really low energy. And if you can see here, this one actually switches to be in units of meters, which means they're very long. 10 to the third meters are very long. But this visible light range here represents such a small portion of this electromagnetic spectrum. So the reason why this is important is because wavelength corresponds directly to color. The wavelength of your light that's given off is essentially its color fingerprint. It's its identity. So if I go back up to our notes right here, you can see that if I have an emission, I'm going from a high energy state back down to a lower energy state. I'm going to release a lot of energy because it took a lot of energy for me to absorb it to go back in. So if the light that's getting emitted here, I can represent it with an arrow, and it's going to have a very short wavelength. The peak to peak distance is going to be very small because it's a high energy wave since I'm releasing a lot of energy. So I'm just going to represent that like this and say that it has a short wavelength. I'm going to abbreviate wavelength using its symbol. So we give it the Greek letter lambda. It looks like this. So lambda is wavelength. That's the name we call it. So then if I take a look at my red arrow here, the red arrow is falling a shorter distance from n equals 3 to n equals 2. This means it is a lower energy emission. So if something has lower energy, it's going to have a long wavelength. So I'm going to represent that arrow emission like this. And now my peak to peak distance is much longer. So if I go back down real quick to look at that electromagnetic spectrum, this is going to be your long wavelength side. This is going to be your short wavelength side. So things that are in the reds have very long wavelengths, which means they are very low energy waves. Things that are in the blues and the purples, they have short wavelengths, which means they are high energy transmissions. So why does the light release from electrons come in different colors? Because it depends on the amount of energy that's being released. So the wavelength is directly related to that amount of energy. So we're going to say that the amount of energy an electron releases is proportional to, this is the symbol for proportional, the wavelength of light emitted. And our wavelength represents our color fingerprint.